Good afternoon, everyone. I'd like to thank you all for joining us today in our continuing education series. Today our featured topic is Fiber Optic System Design, Part 1. My name is Jessica Petrovoy, and I'm the Marketing Coordinator at fiberoptic.com. Fiberoptic.com is a leading provider of fiber optic products, training, and rental equipment, and we are pleased to present this topic to you today. Before fiber optic networks can be constructed, they must be properly designed, and once they're constructed, they must be managed. Efficiency in these processes translate into lower cost for layout and construction, more productive system migration and field operations, and lower optical loss budget, and also a greater business profitability. So the key to good design is in the questions you ask. With us today to talk about network design is Terry Power. Terry is one of our senior instructors and a field technician with over 25 years in managing and testing networks. When Terry is finished, we will take questions from the GoToWebinar question box at the bottom of the screen for a question and answer session. Remember that our webinar series are recorded and they're available to you online at fiberoptic.com/webinar. Today's webinar will be available for on-demand viewing within 1 week. Thank you again for joining us today, and at this time I turn the presentation over to Terry.
And good afternoon, everybody. This is Terry Power. As Jessica said, I started doing this about 25 years ago. I started working in fiber optics and cable television in 1987 and kind of grew up with fiber optics. Spent some time living in the islands, was outside plant coordinator for Tele Barbados before joining the staff here at fiberoptic.com in 2009. In 2011, I was named one of the senior instructors, and now I'm also the international training manager, and we do these webinars together every month. So again, I'd like to welcome everybody, and let's go ahead and talk about fiber optic system design. This is part 1 of a 2-part series we're going to do in the next month or two. So today we're going to talk about the first half of this, and we're going to talk about planning a network, operational requirements, fiber types. We're going to talk about physical and environmental requirements, inside plant routing and outside plant routing. So planning a fiber optic network. The first thing we're going to want to do is a feasibility study. And as Jessica mentioned in her intro, the key to any kind of good design is in the questions you ask. And if we can learn to ask the right questions, then we can take those answers and use them to create good design. The first question we have to ask is, what are we trying to transport? Is it going to be SONET or SDH, Ethernet, fiber to the home? What are we trying to carry on this plant? How far are we trying to take it is going to determine if we're going to use fiber or copper. Are we going to upgrade the existing system and try to add new services on the existing fiber, or are we going to have to install new fiber optic plant? If we decide we're going to add new plant, what are going to be the rights of way cost, hub location costs? Are we going to lease or buy these locations? Do we have existing pathways, or are we going to build new pathways, or are we going to lease them? All of these questions need to be answered. And then if we look at aerial plant, we're going to be looking at pole attachment permits, make ready, and everything that goes into hanging new plant in the aerial environment. So some of the operational requirements. First thing, again, we have to decide is, what are we taking down the road? Are we going to have voice, video, data, telemetry, fiber to the whatever, fiber to the home, fiber to the curb, whatever we're calling it? or some combination of all of these. As you can see in the drawing, fiber to the home is actually a combination of video, voice, and data. So what we're trying to carry is going to be the first key in understanding our needs for the physical plant. Then we need to look at the protocol or architecture. Token ring, Ethernet or Gig-E, or we're going to put asynchronous transfer mode on there. SONET or SDH, fiber channel. Is it going to be hybrid fiber coax, where we go back to coax and deliver that to the last mile? Or PONs, passive optical networks, fiber to the home. Then we need to select the standards. We need to look at transmission standards for the protocols. Again, SONET or SDH, fiber channel, passive optical networks. We need to look at the installation standards. In the United States, we might look at EIA-TIA 568C and 758. If we're looking at more of an international standard, or if you are operating overseas outside the U.S., you would look at ITU-T G.983 and 984. And then when we look at our testing standards, the IEC 61280 or 14763 are just two of the possible testing standards for our networks in the field. Then we're going to select a wavelength. And the wavelength is going to also determine how far and how fast we can go. Are we going to use multi-mode? Is this a short distance? Maybe you're designing inside a building. You're going to want to work with multi-mode, at least for delivery to the last switch or to the desktop, depending on if you're pushing it all the way to the desktop. And you're going to be looking at 850 or 1300 for your wavelengths. With single mode, you're going to be looking at traditional 1310 and 1550. With fiber to the home, you're going to have downstream 1490. Are you going to be working with CWDM or DWDM, coarse wavelength division multiplexing and dense wavelength division multiplexing? In either of those cases, you're also going to want to use single mode discrete lambdas or specific wavelengths in your wavelength division multiplexing. What data rate? These are all questions that we need to look at on the front end. So what data rate are we going to be looking at? DC, a direct connect, are we looking at Ethernet? A SONET or SDH, are we running 10 gig or even up to 40 gigabits? All of this is going to affect cost and how we design. So we're going to be looking at fiber types and some of the fibers that go with the particular wavelengths we've already discussed. Of course, multi-mode for indoor is the original fiber type. It has the larger core, and then we've got single mode, and we're going to talk about all the variations of both of these. And single mode, of course, has the smaller core and the longer distances and higher data rates. So again, multi-mode was the original fiber type. It's used in local area networks, short runs, uses an infrared LED, which is relatively low in cost, or a vertical cavity surface emitting laser, or VCSEL, that uses, it's a much tighter beam and functions essentially like an LED, but it's more powerful and has a tighter beam, and we get a lot further distance with these, but they're also more costly. And it also, multi-mode, of course, has multiple paths or multiple modes. Okay, so we've got in the fiber types of multi-mode, we've got the old legacy multi-mode, the OM1 and OM2. OM1 is that 62.5 micron core. OM2 is the 50 micron core. And as you can see from the chart, OM1 and OM2 have very short ranges at 10 gig. If you're trying to push anything more than 10 gig on OM1 or OM2, you're going to be pretty much shackled. And you're going to have to look at either shortening your spacing, putting in more switches, or going to the higher cost of VCSELs and then the OM3 and OM4 laser optimized type of fibers. Now with the laser optimized, it is a graded index which will cut down on modal dispersion, and it will give us the ability to push out to about 300 meters with a 10 gigabit link. And then OM4 will allow us to go out to 550 meters on that same 10 gigabit link. Now both of these have the 50 micron core, which also reduces the number of modes available, which reduces modal dispersion. So both of these are designed for use with a VCSEL and the higher power and the higher bandwidths, which allows us to push out to those hundreds of meters rather than 33 or 82 meters. The legacy OM1 has a numerical aperture of about .275, and as you can see here, we've got 1.5 dB of attenuation at 1300, and at 1300 we can also push somewhere around 500 megahertz per kilometer. OM2 is going to have a numerical aperture around .2, reflecting the smaller core size. The losses get much better here at 1300. We're only looking at .8 dB per kilometer, and bandwidth up around 1,000 megahertz or 1 gigahertz per kilometer. And then OM3 and OM4 also have the 50 micron core and the .2 numerical aperture. Losses are down to 0.6 for 1300, and some pretty significant bandwidths at 850, 2000 and 4700. They're still going to be around 500 megahertz at 1300. Now, single mode. Single mode is used for wide area networks, backbone systems, long runs, laser for a light source, and we're talking a true laser, and has a single path of light or a single mode. So some of the fiber types here, we've got the ITU-TG.652 family of fibers. These are all considered OS1, 652, 52A, B, and C. Pretty much standard single mode fiber. Then we get into the 652D low water peak, and that's classified as OS2. Then we move into the 653, which is dispersion shifted, moving our point of zero chromatic dispersion up to around 1550. Then the 654 is cutoff shifted. 655 is non-zero dispersion shifted. This takes care of the water peaks and also shifts the zero dispersion point to around 1490 or 1500. And this opens up a lot of opportunities for DWDM. Without that water peak, we can use the entire spectrum. And it also tightened up on a lot of the core geometry issues that were causing polarization mode dispersion in old legacy outside plant fiber. And then we've got G.657, which is a bend-in sensitive fiber. while I've seen this used a little bit in the outside plant, this is typically used for patch cords and for inside plant after the transition and before it gets to the patch panel. So again, you'll see patch cords that have a bright blue color. It's kind of a darker blue, and those are the bend-insensitive patch cords. If you see aqua patch cords, those are going to be the laser optimized multi-mode. So just make sure you're looking at aqua or dark blue on those patch cords, dark blue being the bend-insensitive. So looking again at the 652 through 652C, had a mode field diameter of 9.3 microns, numerical aperture of about 0.13, attenuation 0.25 at 1550. The problem is it had 17 picoseconds per the nanometers kilometers at 1550. And while the loss is dramatically less at 1550, we had an incredible amount of chromatic dispersion at 1550, making it unusable for long runs. And you can also see from the chart the 652D low water peak is the one with the little bump. If we had zero water peak, it would be that solid gray. And the 652 family up through 652C has that huge water peak there around 1380. And that effectively killed an entire section of the spectrum and made it unusable for CWDM or DWDM networks. So physical requirements and environmental requirements. This is the point where we start looking at the outside plant. We start looking at the map. We start looking at the routing inside our building. We're going to start developing the path that it will take. In the outside plant, we're going to look at distribution hubs and cabinets. In the inside, we're going to be looking at our comms rooms and communication closets. In both cases, we're going to look at whatever splice enclosures we need and where we're going to place them and what enclosure do we want to specify. Then we've got to look at the electronics locations, COs and head ends, nodes, any repeaters or regeneration sites. All of that has to be looked at in our overall design as we start to look at maps or in drawings. Now we've got to ask another question. Where is the fiber going to be placed? Aerial, it's either going to be lashed or self-supporting, or like these drawings, are we going to have underground cable? Are we going to use a single interduct like the picture on the top? Or are we going to use a duct bank of rigid PVC between our manholes, as you see in that lower picture? Or are we going to direct bury? And I will tell you up front, direct buried is probably my least favorite of all of these options. Too much potential for disaster, no protection for the cable. You need to spend the extra money to get armored. So all of these have to be offset against cost. And next month, when we talk about part 2, we're going to be looking at costing issues. So you'll see that, and you'll hear that a lot of the comments that I make are going to be about cost. Now, in the inside plant, are we going to use interduct, cable trays, cable runs, ladder racks? You know, what kind of tray are we going to use? If we use duct, we've got to look out for fill ratios. If we use cable trays, such as the one that's shown here in the picture, we have to consider how much fiber can we put in it, how many fibers are we going to add to it later. how much are we going to need to change it? If we've got a lot of fiber already installed on the bottom, we lay more on top, then we want to remove the old stuff. How easy is that going to be with whatever route you choose? You know, if you pull it through interduct and then you want to take out the legacy fiber and get it out of the way and run off the new plant, well, you're going to have more problems than, say, if you use a tray or trough like this in the drawing. So all of these have to be weighed against the future. You know, we always have to plan for the future. And I'm not sure if this is mentioned, and now's as good a time as any, talking about the future. I have seen estimates of anywhere from 35 or 40 years to 75 years on the outside plant life expectancy. And if it's installed correctly, you may be looking at 40 to 70 years of lifetime. And while I'd like to be around to see the end of that, we've got to look at whether or not what we're hanging now is going to last into the future. Is it going to meet our capacity needs? Bixby says that the life expectancy of a commercial building is about 70 years. The life expectancy of the technology is 5 to 7 years. So 10 to 14 times in the lifetime of a building, the technology is going to completely change. And one system is going to be completely obsolete. When we design our fiber for tomorrow, are we designing it just for tomorrow, or are we designing it for 5 years from now, 10 years from now? I can't stress strongly enough how important I feel it is to design in 4 times what you think you need, because you will ultimately need it. So what kind of environment? Now, in the inside plant, we're going to have a consistent environment. Temperature, humidity, some amount of dust control. All of that's going to be present in the inside plant environment. The thing is, you've got a whole lot more possibility for multiple moves, adds, changes, rearranging the cubicles, and then suddenly you need all the fiber to be in a different place. On the other hand, with the outside plant, it's hard to perform these moves, adds, and changes. But, and then you also have a very harsh environment. Temperature, winds, storms, lightning, ice, backhoe operators or tractor trailer drivers, any number of things to cause potential problems later. And then our indoor versus outdoor cable considerations. We've got to look at temperature changes, weathering effects, ease of access to the cables. This is a big one. Now, that ease of access, we have any number of places that I have worked where, for one reason or another, a manhole was covered, or a manhole or cabinet was placed where they don't snow every 3 days for about 4 months, and we had to wait for the spring thaw before we could get to the area where we had to work. Doors where there's not a spare key and somebody goes on vacation. Somebody rearranges the cubicles and covers over the access port. Is the access in the ceiling? Have we built a new wall and blocked off access to a portion of the ceiling? All of this has to be considered when we are putting our cable in. what jacket material are we going to use? Some jacket materials slide more easily against each other, and others are going to drag and create a problem with getting additional fibers in. Cable size in relation to the fiber count. This goes to, in the inside plant, whether we're looking at distribution cable, which is considerably smaller than, say, breakout cable, which is a bunch of patch cords all bundled together. We want to look at all of those cable size issues. And then just the fiber placement. Where are we going to put it? How are we going to protect it? All right, equipment locations. Where are we going to put our panels, our racks, our splice enclosures, hubs in the field? Do we have space for these racks inside? Do we need to get more racks? Do we have floor space for the more racks? Are we going to put this in a place where we're trying to cram a bunch of wall boxes into a broom closet and calling that a telecoms room? What kind of power requirements are we going to need for the transmission equipment? Electricity, are we going to need AC or are we going to run off DC? Are we going to need battery chargers? What are the voltage requirements? I've seen stuff running from 5 volts to negative 48 volts, plus or minus 12 and anywhere in between. So we've got to be aware of our power issues. And then again, access to these equipment locations, rough terrain, secured buildings that we can't get into, and then suddenly we can't maintain the plant in the middle of the night. And before I go on to this next section, I do want to remind everybody that the question box at the bottom of your go-to window pop-out window, or go-to webinar pop-out window, too many W's there. That question block is a place that you can post your questions during the webinar as we go along, as they come to you, and then we will get to all those questions at the end. So don't hesitate to go ahead and throw some questions in and get them in the queue, because I'll probably take them in the order they appear in the queue. So if you want to get your question up there first, go ahead and start typing while I'm continuing these next couple of sections. All right, so let's talk about inside plant routing. What do we want to do? First thing we want to do is get the architectural drawings as much as we can find. If we can get blueprints for the building, we win. Do we have as-built records of whoever put in the existing communication cables? If we can get those, we're certainly going to want it. HVAC drawings. Where's all the ducting? Where are the firewalls? How can we get from one place to another in the suspended ceiling, if that's what we want to do, without having to cross a firewall? We want to contact the building owner or manager, and we definitely want to get a tour of the building. We want a site survey, and we're going to carry a camera. And we're going to take pictures of everything. Because as soon as you don't, oh, I'm not going to use that area, then you're going to not take the picture, something's going to happen to your planned route, and you're going to find out that you need to use that area. So record everything. I mean, digital cameras today, I carry a camera in all of my travels, and I put a 32 gig SD card in my camera, and I can shoot 1,000 pictures in high definition. So, it's cheap and easy. And the more pictures you have, the better you're going to be able to design later, because unless you've got an idyllic memory, you're going to want to have those images saved on the computer somewhere. You're going to want to locate all of your equipment rooms. Find out what routes are used now and look at whether or not you can use that same route or if you're going to have to come up with new routes. Identify obstacles. And again, that goes back to firewalls, existing ducting, existing electrical. You know, anything that's going to get in the way of us using the route we want to take. Fiber management. We hit on this briefly earlier, but are we going to use fiber duct? Are we going to have it strapped to the wall, hanging from the ceiling, or are we going to use ladder rack? You know, that's the old reliable, straight ladder racks. Nice and easy. You can pull a lot by yourself. It's low maintenance to pull. But it doesn't change elevation very well, and it doesn't turn corners at all. You got these, you know, blocky 90-degree turns. Spine tray. And it's just what it sounds like. It looks like in the old cartoons when you'd see the desert in the American Southwest, and it would show the rib cage of a ox or a buffalo or something sticking up out of the desert. That's how spine trays actually look. They usually come in 18 or 24-inch lengths, and they're put together end to end with kind of a hinge joint, and it gives you a lot of flexibility for curves. Since it's hung from the ceiling, it gives you some more flexibility and changes of elevation. Then mesh trays are at their best with a good solid wire, very practical, very customizable. The problem is if you go to the lower grades of wire mesh, I've seen some that were just barely better than chicken wire. And they're floppy and they're flexible, too flexible, and they don't give you the proper support. So you got to look at how you want to control and move the fiber, how you're going to manage it and keep it supported, protected, and also provide for ease of additional cables to be put in. Again, if you can design for 4 times what you think you need now, adding fiber later won't be as big a deal because you just turn on some more pieces of glass. And pulling it once is way cheaper than pulling it twice, 3, 4 times. The extra cost of the fiber count is negligible compared to the labor cost of pulling additional cables later. And then you want to look at your air conditioning and power availability in all of the cabinets and all of the places that you're going to need to have active devices. If you've got a powered switch designed in the ceiling space, you got to make sure that you've got power there to turn it on. Do you have temperature control in the closet that you want to use? Because a lot of these electronics tend to warm up excessively, and if you're not providing a cool environment for them, they get very heat sensitive and will eventually burn out or shut off. If you're lucky, they just shut off. So, outside plant routing. Well, just like with the beginning of the inside plant, we're going to obtain drawings, preferably topographical drawings. We're going to want street maps, or a street map overlaid onto a topo map is really the best possible, best of all worlds. Also, Google Earth or Yahoo Maps satellite view will give you a great deal of idea about what an area looks like. So when you're designing, you're not designing across a ravine or through what looks like a simple state park or something, or along the edge of a state park, and it turns out that it's some kind of forested area that's going to be a nightmare to work through. All of this you can get from maps and Yahoo Maps and satellite views for free nowadays. Are we going to go aerial? Or are we going to go underground? Are we going to direct bury? Or are we going to put it in conduit? My preference is always conduit. Then we start drawing the route itself. We start drawing on the map and trying to figure out the best way to get there. Generally the shortest possible route. But then we're going to take that and we're going to go walk it out. We're going to take pictures of everything along the proposed route. If we're looking at going aerial, we're going to want to take pictures of any kind of make-ready, any obstacles, maybe a railroad crossing or a highway crossing where we maybe need to set new poles. If we're looking at underground, we're going to look at our manhole locations. We're going to look at where do we need to obtain a right-of-way, how safe is it going to be to work along that. That proposed route, are we going to be able to get off the road, or are we going to be in the middle of a highway while we're doing the work? Any number of things that you could find, and the 1,000 things that I can't even think of, are the reason that we have to do walkout and we have to take a lot of pictures. I went out on a splicing job a couple of years ago, and on the map in 2 dimensions, that nice sweeping curve looked like the road went up and then gently curved around an obstacle. Looked like maybe it was going around a building or something. Well, when you get out in the field, you realize that it doesn't just go straight and then curve around. It goes up a rise. When you top the rise, you see the road in front of you. And it's not until you start on over the hill that you realize that the curve is there. And it's like a roller coaster ride. And then in the outside of that curve, on a road that's just barely wide enough for 2 buses to pass when they pull in their side mirrors on the school buses, with no shoulder, that's where my pole is that I'm supposed to put a 288 count splice. Obviously that was not a good day. And had someone done any kind of walkout or record keeping, they would have looked at that and said, no. That is unsafe. So walkout has got to be done so that we know that we're putting it in a good location, a safe location. Because not only do we have to do the work the first time, we might have to go back and do maintenance. And we've got to make sure that the locations we select for our splices and cabinets and everything else are in fact safe, usable locations. And again, permitting, I've already mentioned permitting in the underground, rights of way, permitting on the pole, any kind of make-ready. We might get somewhere and find out that we're going to have to move everybody up, or if we're the low man in communication space, and and the guys at the bottom right now are barely making clearance on a highway, then new poles are going to be set. We want to record all of that. And then the other thing that we have to consider as outside plant designers is we actually do have a little bit of inside plant on each end, because it's still ours until we get to that transition box. So we've got to look at that and how we're going to make entry into the buildings at the beginning and the end of the fiber run. Last topic on the routing, and the last topic for today actually, so make sure you get your questions in the question box at the bottom of your GoToWebinar window. We've got to look at what level of route protection do we want in the outside plant. We're just going to run it point to point and leave it unprotected and just count on doing some emergency restoration? Are we going to go with 1-to-1 protection or 1 to however many? You know, are we going to have multiple diverse routes? If we're in a ring architecture, that's all well and good, but if we're doing a point-to-point link between two buildings, we might actually want to put 2 separate routes following, you know, as much diversity as possible, so that if one gets knocked down by a tractor trailer or dug up by a backhoe, then we've got an emergency route that is always available, that will either auto switch or can very quickly be switched over to, providing us some kind of protection against an outage and minimizing our downtime. So I guess that depends on the critical nature of your circuits and service level agreements with your clients, etc. So, and battery backup. What kind of power protection are we going to have? Secondary power supplies. Are we going to have a generator? Are we going to try to use wind or solar? You know, emergency generators, probably the old standby, you know, big Onan, you know, diesel engine running a generator outside the building. And you can switch over to that fairly quickly. A lot of them now have switches that if it loses primary power, it will auto start the diesel engine and power up the generator. Most of our head ends these days have some form of battery backup that will allow us at least a couple of hours to get the emergency AC restored or emergency power turned on. One thing about emergency power supplies or emergency generators, I had a job where they had recently had a lot of damage from flooding from a hurricane. And they wanted to put an emergency generator at one of the head ends. And they wanted to just set it out on the side of the parking lot. And I said, well, that's fine. What, you know, who's going to build the stand for it? Because I presumed that we were going to elevate it at least above where the mud marks were on the side of the building, indicating the level the water had achieved during the last flood. I just don't want a saltwater inundated diesel engine being my emergency backup power. So I actually left that job shortly after that. They just didn't want to listen to any of my experiences, and they insisted on putting it on the ground. You want to be aware of the location of your emergency generators. If it's in a flood-prone area, make sure you've got it up on some kind of elevated platform so that you don't have saltwater inundation or flooding of your diesel engine. And then you want to look at your standby equipment. Are your standby circuits going to be hot? Are you going to have hot swappable modules where you can change out perhaps a DWDM discrete lambda transmitter without having to take down the whole system? Now it's going to be more expensive. So again, it's all going to be a matter of cost and where your cost and price point is. So this brings us to the end of part one. Next month, during the part two and the conclusion of this webinar and this presentation, we're going to look at choosing the components that we use, calculating a power budget. We're going to talk about testing and documentation, some preliminary cost estimating, and then some practical considerations and a wrap-up. So again, that's all next month. The date has not been set, but you will be getting notifications just like you got the notification to this one. So again, thanks everyone for being with us today. Let's see, I've got some questions, and if you do have additional questions, please get them. Get them into the webinar or the GoToWebinar question box. Let's see, what have I got here? And I'm going to read these, so bear with me while I'm trying to read and talk at the same time. My ability to multitask is limited. So I want to distribute DirecTV satellite signal to 300 plus units of a building. We want to use single mode over a PON, but can't find a PON that will go over 1 gigahertz. DirecTV requires 2.2 gigahertz plus. Do I have any suggestions? One suggestion would be to put in a head end at your receive site. Receive all of the signals and then look at how you want to distribute that through the units. If you go ahead and process it and get the raw video and raw audio, go ahead and get your channel information. Then you can go ahead and process that and then recombine it and insert it. We've got a couple of people here that do a lot of work with passive optical networks that could assist you. So if you want to give us email at training@fiberoptic.com, we can get a few more details and dig into that a little bit with you. Perhaps even talk about coming out and doing a little consulting work for you on site. So again, that is going to be training@fiberoptic.com. Now, between the second question, between the G.652D and the 675, is there a big difference in performance? You know, I think yes. The biggest difference when we get up into NZDS type of fibers is in the long range and polarization mode dispersion. The NZDS has a slightly tighter tolerances on core geometry issues of size, circularity, concentricity. And those sorts of issues, any of those asymmetries within the core can cause polarization mode dispersion. The 652D doesn't have quite those tolerances. Also, it depends on the type of work you're doing. If you're going to be going with a single wavelength, the 652D might be okay for you, particularly if you're going with 1550. When you get into opening up the entire spectrum, you want to look at your chromatic dispersion as well as water peaks and that sort of thing. So I guess it depends on what you're trying to do with it. They have very different applications. The 652D, I think, still has lambda 0 closer to 1300, whereas the 675 is going to have a lambda 0 up closer to 1500. So depending on length and wavelength, that's going to be your determining factor. All right, we got another question in here. Will we be covering FTTX networks in part 2? We're going to talk a little bit about it, but this is an overview of fiber optic system design. We have a 4-day class that we teach, and this is honestly 2 one-hour webinars taken out of a 4-day class. So our ability to get into a tremendous amount of detail in this venue is somewhat limited. So while we will mention some about FTTX, it's going to be very much of an overview, and we can definitely get together on classes and training and questions that you might have. Again, you can email training@fiberoptic.com, and I'm also being notified that we're going to add that to the topic pool for possible future webinar topics, and maybe get into just a little 1-hour presentation on FTTX networks and design. So I'm not seeing any more questions. I'm going to ramble through my thank yous again and see if any more questions pop up in the question box down at the bottom of your GoToWebinar window. And thank everyone. You guys have growing support for these webinars, and it's exciting. You have a lot of things you could be doing with your day, and you've chosen to spend time with us. And we're honored and we appreciate your time. And I don't see any more questions coming up. So I'm going to say good day and wish you all the best. And this will be available on demand about a week from today. And hopefully by then we'll have a date nailed down for the part 2. But look for it coming in May. Oh, wait a minute. One more question. You just caught me. Let's see. Someone is talking about different fiber types, and single mode uses G.652D extensively. Will this work well with DWDM? Up to what distance can we get away with this on DWDM? I wouldn't even start trying to put DWDM on that. I would go for NZDS at a minimum before I tried going with any kind of dense wavelength. You start putting those little 8 micron wide lasers, and depending on how many you want to, how many discrete lambdas you want to put in there, you could be running into all kinds of issues of dispersion and water peaks and every other thing. So while working with a single wavelength, particularly around 1300, is pretty good with the 652 family, I wouldn't try to go anywhere near DWDM until I got up around NZDS type quality fibers. So again, thanks to everyone. We appreciate your time. You have a great afternoon, and look for this on demand in about a week. Have a great day.